Hi, Chetan, can you see me? And someone let me know what's the
Yeah, we can see this, sir.
can you see the whole screen, or it is the
whole slideshow is visible, Shiv.
Visible, sir.
it's not like the presenter mode.
It is full screen, not presenter mode.
Okay, good. Okay, so I will start the lecture now. We're going to start with it's 26th January. Happy Republic Day to everyone. We're going to start with a very difficult topic, which people find it very difficult. So we'll be talking about first part will be about electricity, and then a bit about electrical safety. There's a whole section on diathermy and electrical safety. That's a chapter on its own, which I will cover some other day. So we'll start with something which is very, very basics to electricity. It's about current, voltage, and resistance. And what's the relation between them? And this is just like flow of water. But there are certain fallacies which have been maintained in physics about electricity. So when we look at any electrical circuit, it is always shown that the current flows from positive to negative. And what is current? Current is basically flow of electrons. But do the electrons actually flow from positive to negative? Not really. So if you look inside a wire which is conducting electricity, you would see that the electrons are actually flowing from the negative terminal to positive terminal. So within the your conducting material, the electron flow from negative to positive. But when we look at the circuits, the way the circuits are described, the current flow is always shown as from positive to negative, just like water flows from high level to lower level. So we'll continue to use that analogy about the flow of water. So first thing we talk about a voltage or the potential. Now you need a potential, so there need to be a gradient, a positive gradient and a negative gradient, or higher gradient, a lower gradient, for anything to flow. So if you have a water tank, then you would have the tank on the top of your building. You could have a tank, in the basement, but then you will require a pump. You need electricity to pump it. So that becomes a potential. But let's keep it simple. So if you have a water tank, you need to place it on a height to maintain the potential or get that potential. So the flow of water will only happen if there is actually a gradient or a potential. So if you place this water tank on the floor, as long as the level of water is above the tap, there will be flow. But if you place it much higher, you will see that the flow is much better because you have increased the potential. So what is the relation between current, voltage, and resistance? Again, it's about Ohm's law, and this analogy will likely help us to understand that. So the current is a flow because the current is defined as flow of electrons. The potential is your voltage. Voltage is the driver for this current. So unless you, in any appliance, whether it's plugged in or it's run on battery, unless you plug it in, and there is a driving force, the driving force is the voltage. And in this case, resistance is a tap. So if you close the tap, the resistance is very high and there'll be no flow. You start opening it slowly, and then the flow occurs. And when it's fully open, the flow is in full blast. So the flow of current is dependent directly on the potential. Like I said, the higher the water tank, the greater the force of flow of water. But it is inversely proportional to the resistance. The lower the resistance, the greater the flow. So the flow of current is equal to V by R. That's what is Ohm's law is. And you can rearrange this and say that, R is equal to V by I, or V is equal to I into R. There are different ways of looking at it. So how is the power supply, or where does this potential comes from? Okay, we know that if something is battery driven, it requires a battery. As long as when the battery dies, you need to change it. But that doesn't happen at home most times. So the electricity comes from the powerhouses. There can be thermal powerhouses, hydroelectric powerhouses. So this is on the way from the, I traveled from Liverpool to Manchester. This comes on the way to Manchester. And this I had taken many, many years ago, these photographs of this thermal power station. So the wires from the power station don't come directly to homes. They go to a substation because power stations generate electricity at a very high voltage. So it need to be stepped down. And from the substation, then you get a live wire and neutral wire. The earth is basically a wire which is dug into the earth. The earth is a huge conductor. So there is the neutral wire is attached to an earth at substation. And at home, the earth is attached to the body of the equipment, which we normally have. So I will talk about that in a minute, because that's knowing about earth is equally important for safety. So when you, for example, you plug in your toaster, there's a live wire, neutral wire that goes to your heating coil, heats it up, and you put your toast in and it gets toasted. But the earth is connected to the body of your toaster. It doesn't do anything with the functioning of the toaster, but it's important for safety. And we'll discuss about the role of earth in electrical safety. When we talk about the voltage, it's not the peak voltage you're talking about. We talk about RMS, or root mean square voltage. What exactly is root mean square voltage? This is commonly asked in the exams. It's also as part of the MCQ. So, for example, UK main voltage is 230 volts, but this is never constant. It keeps varying between 253 volts to 216 volts. So there is always a variation between the voltage. But what we're talking about here is actually the root mean square value of the voltage. And if you were to talk about a peak voltage will be square root of 2 into 240 volts, that is 340 volts. That is our peak voltage. So what exactly is root mean square voltage? So if you look at the current, which is alternating current, if you square it and then take a mean and then take a square root over that, that becomes root mean square voltage. Okay. So that's how the RMS is derived. And when we talk about 230 volts or 120 volts, that is a root mean square voltage. Okay. So that is a root mean square potential. For exams, again, we need to know about various components and applications of them. And I'll start off with this. So you have an emergency trolley, and on this, you have this equipment, the defibrillator. Everybody knows how to use a defibrillator. You attach the pad, you increase the voltage on it, and shock the patient, and voila, the patient is back to normal rhythm. You have actually saved a life. Well, how does a defibrillator work? What are the components within a defibrillator? Okay. The defibrillator is powered with 230 volts, but this voltage is stepped up to 8,000 volts. And the first thing it does it when you have it on the charging mode, it charges the capacitors. So we need to know about capacitors. But when it goes on to the patient circuit, the capacitor, the current from the capacitor flows through a diode and an inductor. And again, we're going to talk about them, why you need to actually have a diode and an inductor and a capacitor within the circuit. So this is a very simplified circuit for a defibrillator, which everybody need to know for exam purposes. So the main component of the defibrillator is a capacitor. The capacitor is something that which stores the charge. And people find it very difficult to understand. How can a capacitor store a charge? And a capacitor is nothing but, if you look at it, there is conducting material separated from non-conducting material. So there are liquid capacitors, there are fluid capacitors, there are paper capacitors. How do they actually store charge between two plates? And this is toilet, and a cistern. So you have a storage tank, and then you have the tank, which is the flush. So in case of the capacitor, the flush represents the capacitor. Okay, it needs to be filled up from a storage tank. Every time you want to use it, it needs to be filled up. So in the same way, whenever you want to use a defibrillator, need to charge it. Okay, so the charging happens from the main voltage. If it is disconnected from the main voltage, you cannot actually charge it. So capacitor basically has two plates, which are conducting plates, and these are separated by paper, air, liquid. And when you apply a charge onto that, it gets stored within the capacitor. And then you can disconnect it from the main charge and use it on a patient. Okay. So how much charge does a capacitor hold is directly proportional to the voltage. And the capacitance is equal to the charge over the voltage. So when you talk about 1 farad is equal to a charge of 1 coulomb over 1 volt. So you need to remember this definition. And the energy stored, that is energy stored within the capacitor, is half of the Q, that is the charge into the voltage. But we also know that the charge is a product of the capacitance and the voltage, and hence the energy stored is half of the capacitance and square of the voltage. This again is important when you want to actually explain how you charge a capacitor in a defibrillator. So this graph is very, very important to know. You can actually put in some values into that, and this will give you the answer why you need to charge or step up the voltage from 230 volts to 8,000 volts for a defibrillator. The answer will come from this. And for that, you need to know what is the capacitance of the capacitor used in the defibrillator. That's in another lecture. Okay. But capacitance can cause interference. So for example, this is not the newer types of the lighting within the theaters. Most of them is now LED type. There's an old type thing where you would have a conductor. And the body also is a conductor. So now you have actually built a capacitor. So there are two conductors separated by air, and that's become a capacitor. So when there is a flow of current, the alternating current through this conductor, and that will get transmitted, this capacitance is for. And because it's an alternating current, the capacitor is getting charged and discharged, and this creates interference within that. So you get interference on the ECG. So capacitance can cause interference within the ECG. The next component we're going to look at is inductors. So what are inductors? Inductors are nothing but a coil, okay, of a conducting material. As a student in school, you would have actually played with electromagnets, where you take an insulated copper wire, wrap it around a nail, and connect to a battery, and you create a magnet, electromagnet. But if you were to, instead of the direct current or for powering it from a battery, if you power it with an alternating current, what you see is that this causes a magnetic field, alternating magnetic field within the coil. So if you put a rod now, through a metal rod through this coil, you will have a alternating magnetization and demagnetization. So these are what inductors are. And inductors are part of your defibrillators, but how they work is totally different, and we'll come to that. Okay. But inductance can also happen within the operation theaters. And of this, diathermy. So when we talk about diathermy, we'll talk about how the diathermy work, and these are important source of interference in the theaters. Every time the surgeon buzzes to coagulate a bleeding point or cut through the skin, you see interference on the ECG, and that's happening because of this, great amount of the electromagnetic interference which is happening from the diathermy. Okay, you see every time you see, and it really disturbs you a lot again, because you can't then sense what is going on the ECG. So interference happens because of inductance. So diathermy machines, unfortunately, they need to be kept closer to the patient. Ideally, it should be as far away from the patient as possible. But the inductor on its own within the defibrillator circuit has got no meaning until as it's in the series with a capacitor. And it is this circuit, which is also known as an oscillator, which is important to maintain the delivery of the shock to the body. So when the capacitor circuit is now on, the current will flow through the inductor, and because of the alternating magnetic field, this will again charge up the capacitor. Okay, and this circuit will keep going on and on till the current actually completely dies. So what you're doing is that you are increasing the duration of the energy delivered to the patient while you shock them, and this is very, very important. If the energy was delivered for just a few milliseconds, the only thing it will do is cause burns on the skin. It will not be conducted to the heart and cause defibrillation. So it's very, very important that this oscillation is maintained. We also talked about that the current, the voltage, not the current, the voltage need to be up from 230 volts to 8,000 volts and your defibrillator. So, and this is done through the transformers. Okay. So transformer basically consists of two circuits, which is the primary coil where you would attach the main power. And because of the inductance, again, so this is about inductance, you can induct current. That's only possible with alternating current. You will not do it with direct current. You have to remember that. the transformers will not work with direct current. When you have direct current, you just form electromagnet. So you need to have alternating voltage to induce current in a secondary coil. So the voltage, say if this is a primary voltage VP and you have the number of coils in the primary is N and the secondary coil is S, and the voltage in the VS can be calculated. So the voltage in the primary by voltage in the secondary is equal to NP by NS. So the voltage in secondary is equal to VP into NS by NP. So that's the equation to know whether it's going to be a step up or a step on transformer. So, if this case, we have got 3 coils in the secondary and we got 6 coils in the primary. And if the voltage applies 240 volts, then the voltage in the secondary will be 240 into half. So it'll be 120 volts. So it is half. So this is a step down transformer again. So if you have the same number of coils, 240 volts, you will produce 240 volts with the same number of coils. If you halve it, you halve the voltage. Okay, this becomes a step down transformer. But if you increase the number of coils in the secondary, you can increase or double it, and this is called a step up transformer. So that's what the defibrillators use. They use a step up transformer to increase the voltage from 240 volts to 8,000 volts. So transformers are an important part of the defibrillator circuit as well. Then we also saw that there are diodes as well in the circuit. So what do diodes do? So if you have a diodes in circuit, so if you have alternating current, what it'll do is it'll only allow your positive waves to form through. Okay. So it's like a one-way valve. It will only allow current to flow in one direction. And that's very, very important in these cases. Yeah. Diodes are used as a rectifier bridge where you use the 4 diodes in a particular manner. This is like your Wheatstone bridge. And by doing that, so if you had a single diode, what you'll have is when you have a positive wave, you'll have a positive wave there, okay, going through that. And when you have a negative wave, what will happen is that if there was a single diode, there will be no wave. So you'll have like a flicker. So you will cause a flicker if you have only one diode. But if you have diode in this way, what will happen? It converts a negative wave into a positive wave. And thus, a bridge rectifiers can be used to convert the alternating current to direct current. Okay. And that is again also an important part, which is, diodes are an important part of defibrillators for this reason. They need to have the current flowing through one direction, and it need to be constant. So that's what the rectifiers are an important part of your bridge of the defibrillators. So I've already talked about this circuit briefly. We'll go through this again because it's an important part of examinations. So when you charge the defibrillator, what happens is that 230 volts or 240 volts, which we have, it is stepped up to 8,000 volts. This charges the capacitor. And you apply the pad, and then it say, everybody stand away, disconnect the patient from oxygen. You go onto the charging circuit, you press the 2 buttons on the paddles. It doesn't happen nowadays. It's all attached to the patient. The pads are attached, but that's what used to happen. We used to have paddles. We switch in both hands. You switch them on together, and the current will start flowing through that whole circuit. And you have, converted the patient from ventricular fibrillation to normal sinus rhythm. Now you see that we have monophasic and biphasic waveform. And when I was talking about the diode and the inductor, you have to see the inductor. Now that diode, inductor, and capacitor. So capacitor will charge the inductor then charges the capacitor, and this circuit goes on. And because there is diode in the circuit, the flow of current will be only in one direction. Okay. And because of this oscillation between the inductor and the capacitor, the current is not just a peak, it is spread over certain times, okay? And that's why it is called a damped sine waveform, because with every circle of current, it will slowly, you will lose some energy and it will slowly get damped. So that's why it's a damped sine waveform. So instead of the current flowing through just a 1 to 2 milliseconds here, and now the current flows through the body for around 4 to 8 milliseconds. And this is important because this time is required for the applied current to flow through from the skin to the deeper tissues like the myocardium. And if we could increase this duration further, and that's what happens in case of biphasic defibrillators, you will see that the amount of current delivered, the duration is around almost 12 milliseconds. And there are various waveforms. Again, you need to know this for exams. So you have the truncated, biphasic truncated exponential or BTE waveform, which is used by Smart or Philips defibrillators. And then you have the other one, which is a rectilinear biphasic waveform, which is used by Zoll. But both use the fact that the duration of the current, the energy delivered is increased over a certain period of time. So if they show you the graph, you should be able to identify them in the exams. Okay. Then we move on to something more, you can call it that you do it in day-to-day life, but it's a lot more complex than you think. And this is the biological signals. We monitor ECG, the amount of the current which is produced by the heart is very, very small. It's minute. But we are able to actually get it onto a graphical form on a ECG monitor. How do you actually do that? Okay. So we need to be able to amplify those small signals to see a good waveform. And we all know about amplifiers. You use amplifiers to amplify sound. The better the amplifier, the better the quality of your sound. But if you have a poor quality amplifier, as you increase the volume, as you get to the higher volume, you see zoning. Okay. There's a lot of disturbance. Now that's not a good amplifier. But if you have an amplifier by Bose, you keep increasing the volume, the quality of the volume is maintained. So amplifier is a device that responds to very small input signal, which can be in the form of current, voltage, or power, and delivers a larger output signal. And this output need to contain the essential waveform features of the input signal. So they should not lose the quality of the input signals, which might be very, very small. So when you amplify it, they should maintain the same characteristic. And that's what the good amplifiers do. Okay. Whatever it's the input, the output is almost the copy of that, a true copy of that. So that's what an amplifier is. Okay. So look at these two pictures. We have a small picture. If I have a picture which is not of higher definition, it's a lower definition. If I actually blow up, it becomes pixelated. But if my image is of high definition, the raw image is of high definition, if I keep blowing up, it will maintain the same feature. Okay? And that's what a good amplifier does. And that's what we need for our biological potentials. We need to have a good amplifier. So there are two types of amplifier, the single-ended preamplifier and a differential amplifier. Now, if your machine or a monitor uses single-ended amplifier, the input occurs through one, and then it's referenced to the earth. You will obviously get a signal, there's no doubt about it. But what happens when there is a interference? Okay, so you have a signal, okay, and you have constant interference from that. And this inference is interposed on the input signal, and that's where you get your distortion in the image or the whatever you're trying to record. So single-ended amplifiers are not good for the monitors. What we need is a differential amplifier. So here there is a reference input, but a reference earth, but the input is actually there are dual input. There is a positive input and a negative input. So input occurs between that. And when you have an interference, then the output is not affected by it because it actually cancels out in reference to the earth. So because the interference is common to both the negative and positive electrodes, it will cancel it out and you get a better quality signal. So these are important. The good quality monitors will always use a differential or balanced preamplifier. Okay. Also needed for a good monitor is filters. Okay. So what exactly are filters? Filters are basically arrangement of electronic components that will only allow those electrical waves to pass through that lie within a certain range or band of frequencies. Okay. And I will explain to you exactly what is a band pass filter because that's what most monitors use. So let's say we have, now this has got big holes and you have got some water which has got some dirt. What it'll do is that it'll allow small amount, the particles to pass through, but it will keep the bigger size particles away. So you filter out the bigger particles. But what if you wanted to clear those smaller particles as well? You wanted a clear fluid. Then what you would need to do is you would need to actually take another sieve which has got finer holes. So you need to change that. Okay? When you do that, we're able to do that. So these are what filters are. Okay. So there are two types of filter. And the first one is that as the frequency increases, the output increases as well. And these are known as high pass filter because they're allowing high frequency current to pass through. They don't allow low frequency, but allow the high frequency pass through. And then there are other filters where as the frequency increases, the output decreases. And these are known as low pass filters. Now, if you were to actually combine these two filters, so you have the high pass filter and low pass filter, then we would create a certain filter called a band pass filter where we can limit the frequencies. So what we get is that you will take away the frequencies below certain range and also frequencies which are on the higher range. And you can actually set those frequencies within which the monitor will function effectively. So this is called band pass filter. And these are used when you look at the ECG, when you go into the filter mode, you'll find that there is actually monitoring mode, and there is therapeutic mode, there is a filter mode. So you can actually select that and you can then get rid of those frequencies which are interfering with your monitoring. So you can actually see that the diathermy filter, the disturbances from the inductance from the diathermy, you can get rid of them or from them. So band pass filters are an important part of it. And if you have to actually think of it, how do you actually look at it? So when you are listening to a radio, you could choose a particular station. You say, I want to listen to FM, or whatever, 94.6 FM or 105. So that is what your channel is. You're choosing the channel, and that's like a filter. So you're choosing that you want certain frequency with which your radio is syncing with. But then if you're, for example, if you're listening to classical music, so you might want to have it on a low volume, But if you're listening to, say, rock music or jazz, you might want the volume up. So that's what amplifier do. So if you have to talk about filters and amplifiers, these channels are like filters, and your volumes is your amplifiers. Very simple as that. But these are, again, commonly asked question. Now, the other thing which we haven't discussed about is resistance and Wheatstone bridge. Wheatstone bridge are important part of monitoring system, especially when you're looking at monitoring your blood pressure. The transducers have got a Wheatstone bridge. How is the pressure in the blood vessels transmitted and converted to a pressure reading? That's what a Wheatstone bridge does. Okay. So Wheatstone bridge is nothing but special arrangement of resistors. Okay. So there are 4 resistors in that circuit, and you apply a little voltage across it, and it will pass through the resistors which are in series. So R1, R2 are in series, R3, R4 in series, but the R1, R2 is in parallel with the R3 and R4. Okay, so R1 by R2 is equal to R3 by R4. This is what is Wheatstone bridges. And if you then have a galvanometer between the 2 bridges, you can monitor an unknown quantity. How do you monitor an unknown quantity? So what we do here is that you have a measuring. So one of the resistances, for example, in case of a transducer for monitoring blood pressure, this is called a strain gauge. So you have a wire. As it stretches, the resistance on it increases. As it actually comes back to normal position, the resistance goes down. And by comparing the resistance, we can actually measure what is the pressure that is being applied to a diaphragm, which has this part of the strain gauge. Yeah. And I'll give you an example how this is actually done. So R1 by R2 is equal to the voltage, which is then variable voltage, and Rm is the measured voltage across the bridge, okay, or rather resistance, okay. So if you already know R1 and R2, we can then balance the bridge across, because if the resistance changes, it is measuring the resistance, then you can actually change the resistance of RV, so balance out to bring it back to 0. So the amount of the current applied to bring it back to 0, that is what is the change in the voltage here. So I will take it to a very, very simple method of doing it. So look at this balance. So on one side, you have what you want to measure. On the other side, you have R2 by R1, which is we already know. And then we have RV, which is the resistance which we will actually change. Okay. So if we have a smaller measurement, then you'll have to actually reduce. This is what will happen. It will, the balance will tip, and it'll be other way around. We could change the resistance, the RV, to bring it back. So how much amount you need to take away is the measure of the RM. Okay. So let's say let's put some values to this. So we have when everything is balanced out, so we have both sides like 20 kilos, and the RV say is 10 kgs. Now, because on one side you have lesser amount, on the other side is greater amount, what amount do you need to take out to balance it out? Like, the answer is very, very simple. Take away the 10 kilos. Okay. So that's how it actually works. Or you could actually add 10 kgs to the other side to balance it out. Okay. So it's all about balance. That's what a Wheatstone bridge is. It's about balancing the resistances across. So whatever is being measured, depending on whether it increases or decreases, you will have to make accordingly changes within the resistance, variable resistance RV, to maintain a balance. That's what a Wheatstone bridge is. So say, for example, then one side we know that R1, R2 is say 20 kgs, and then you put an unknown weight into that. And then you have got 12 kg of weight. So how much would the other weight would be? So it's simple, isn't it? So to balance it out, you need to add 8 kilos of weight to balance it out. So that's how it works. So this is a variable resistance, or also called a strain gauge, in a transducer. So pressure is applied, the diaphragm moves, the wires get stretched, and so the resistance also gets changed. Okay. That's part of this is the Wheatstone bridge. So, and then we have the variable resistance. The variable resistance need to be changed accordingly to maintain a balance across the bridge. That's how blood pressure is monitored. Obviously there are different other ways of monitoring them. You can have capacitance instead of resistance in a similar way, but classically it is described as a Wheatstone bridge. So R1 by R2 is equal to RP by R, and thus the measured resistance is equal to the variable resistance into R2 by R1. So you can change the or balance out the measured resistance by changing the variable resistance RV. So V is for variability. Okay. Coming to, it's nearly more than 40 minutes now, and coming to the last part, before we go on to a question answer session and electrical safety, you need to remember what is a simple circuit is. Okay. You have a small battery or cell, connect to a bulb, and you have a switch. So unless this circuit is completed, you have the switch on, the bulb is not going to glow, isn't it? And this is very, very important. Unless you complete a circuit, you don't become part of circuit, nothing will flow through you. And that's the basis of the electrical safety. Okay, thank you. I'll stop sharing now and I can come on to the question answer session.
Hi, Shiv. Do you want to ask questions, and then you can randomly
because
people who are
yeah. So I can actually, I don't know if there were any questions on the YouTube or not, and then we can actually go through those, or
not
if
that I know. Just let me check again on YouTube.
if the people who are on the Zoom, if they want, they can actually ask questions directly.
Yeah. I just need to, they can unmute themselves, or because everybody's muted, I'll let them ask the questions. Does it, first of all, thank you very much, Shiv. That was a lovely lecture. It has been nearly a very long time for me to go through basic sciences, and it cannot be simplified as much as you can do it. I think this was the ultimate lecture. I wish I had this lecture about 15, 20 years ago.
I used to give this lecture. So in the Mercy School, so a lot of people who actually have now, a lot of them have become consultants. I used to teach this on the Mercy. I taught this for almost 8 to 10 years. So I used to actually take this lecture.
Yeah.
Yeah. So the people have been through the lecture. These actually slides are from that time. I've only just a little bit brushed them up, but otherwise these slides are from that time.
Okay. Is there anyone who wants to ask a question?
Hi, sir. Dr. Pankaj, sir.
Hi, Pankaj.
Hi, good afternoon, sir. I just wanted to know how would the questions be designed on this part of as in the questions on electricity and physics of electricity. How are they designed? I mean, would there be direct questions on this topic, or would they be asked in context with some as in the instruments, equipments, like that?
Yeah, so what they do, at least in the FRC, is that they can actually give you just a card, or if you're doing online, they could actually put up a picture of this thing, say, okay, fine, identify this electrical component or the symbol or whatever it is. And then actually they take it from there.
Okay.
They've even in the FRC, they could actually show or ask a defibrillator and say, oh, can you explain to me how does a defibrillator work? And if you are able to draw the circuit, that's fantastic. And you need to keep it very simple. Like I said, there are books which will likely, mention in a very complex way. Just keep it very simple.
I think the most important aspect is whether it's FRCA, EDAIC, FANSCA, any exam all over the world, right? I think there is one important message I would like to give is that, images and graphs and charts say 1,000 words, right?
Yeah.
So,
Right.
and as simplified, and you can't get better teaching than this one on electricity. It's a complex topic, not easy to understand for everyone, and if you can explain in the way that graphs and charts and the flow diagrams that Dr. Shiv has shown today, it's about the impression that the examiner gets, that the subject. They don't waste too much time on you. The moment you show the confidence and the way you explain it and way you write it in a graph or a chart and things like that, they will know. They can read between the lines. They can read your body language. Okay. So, it is all about your confidence, how confident you feel, what's your body language. And the confidence and body language comes with knowledge and practice, right? So Dr. Shiva has given you the knowledge here today, and there are plenty of resources online and offline, on books and everything where you can read. Dr. Shiva was also provided with the material. It's available to download and you can read it, right? It's on the Medusis Gas platform. Now, what's important is if you have good knowledge, it will give you good confidence. You'll be able to explain it, right? So the second thing is about body language and how well you explain it, right? Always, and that comes from practicing, okay? Practicing in front of mirrors, having one-on-one practice sessions. So what will happen is throughout this series 1 and ongoing series of EDAIC II, and followed by Dr. Shiv will also start the FRCA exam Viva practice, is that you need to have Viva practice. The more you have, better you will become. Okay. So, I used to, for my fans, I used to have at least a target of I need to have 50 Viva practices before I go to, that was my target. So by around 30, I felt confident. First 10, I used to get only criticisms, which I didn't hold back. That was very useful because there are a lot of things that you need to unlearn. You need to get rid of some of the concept. You need to get rid of some of the habits. You need to kind of that language, body language skills, speaking language skills, the eye contact, expression. There are so many things, and also talking on the topic, right? So you have to gain that experience over 10 to 20 Viva practices. And then in the next 20, 30 Viva practices, you fine tune it, right? So far, Dr. Shiv has given you the knowledge. You try to get more knowledge and practice Vivas. Now, CK is here, Dr. Chetan Manohara. I hope he's listening in, and he can tell you about
Hi, Guru.
EDAIC II Viva. Oh, thanks, Chetan. Yeah.
Yeah, hi. Pankaj, the questions are some of the common questions I'll tell you. There's a question on Wheatstone bridge. There's a question on the Ohm's law. There can be a question on classification of electrical equipment and electrical safety, and safety features of the anesthetic equipment, in which there are a couple of points about electrical safety in that. And of course, there's a question that's usually asked on the diathermy, on the defibrillators. So they're generally very specific. They'll just ask you, okay, can you just tell me how a defibrillator works? So then you will have to, draw the diagram, and you will have to explain as to how a defibrillator works. And unless you draw a diagram, your answer will be incomplete. So you will have to practice all that. It's very nicely given in the Masterclass series, the chapter on electricity. So you can also revise from that chapter.
Okay. Thank you, sir.
Thank you, CK.
Yeah. So with the electricity, like I said, they are usually, they will show you cards and then ask you to actually take on from there. And there are a lot of people who have written these books, have attended my lectures in the Mercy School and taken back the diagrams and used them, obviously without acknowledging that. Oh, that's fine. But these are actually simple. So the next part will actually contain those symbols. That's one of the commonest questions which is asked in the exam. They give you images and then there'll be symbols, and I'll talk about what exactly those symbols are in relation to electrical safety. So it will become a lot more clearer, the second part.
Thank you, Shiv.
Yeah,
You can start the second.
Yeah, so I think we will start because I don't think other people are engaging as much. So what's going on? It's
Start the slideshow and we'll see how it goes.
yeah. I was
coming.
It's not. 1 second. Yeah. Okay.
Beautiful. Thank you.
Yeah. So we'll continue with the second part. There are 3 parts to it. Like I said, the electrical safety and journal, and then there is electrical safety related diathermy, which is a chapter on its own and very, very important. I think it's very important for even surgical trainees, diathermy, safety and electrical diathermy. So how do you actually define electrical safety? What exactly is electrical safety? So when you are asked about definition of electrical safety, it says it's containment or limitation of hazards related to electrical shock. Okay, and it's not just electrical shock. It's also related to explosions, to fires, to damage to equipment of building, which explosion of fires will do. But here we're dealing with only electrical shock, explosions and fires and damage. That's a totally different issue. And fires is actually known, so diathermy with alcohol caused fire. It has happened in the past, nothing new. They are. Explosions are rare, but can happen. And fires and explosion can cause damage to equipment building. That's a known fact. But we'll restrict ourselves to electrical shock. And we talk about electrical shock. And it's not just the patient, but also staff can get electrical shock. You touch equipment and you suddenly feel a sensation, funny sensation going through you. You know that that's actually just a current flowing from the body of the equipment to you. So what we will get is a macro shock, but patients can not only get macro shock, they can also get micro shock. So we will actually then talk about what is a macro shock and what's a micro shock. So when you talk about macro, as the name says, it's a large amount of current which need to flow through a person, which can cause harm or death. Okay. So it doesn't always cause harm or death, macro shock. It can flow through your body and cause you a funny sensation. So it all depends on what amount of current is flowing through it, but it need to be really large amounts to cause harm or death. Whereas micro shock is about very small amount of current. Okay, you're talking about milliamps, small milliamps. Okay, but this is in an electrically susceptible patient. So who is an electrically susceptible patient? So when you define microshock, you need to actually specifically mention this word, that this is small amount of current in an electrically susceptible patient. So electrical susceptible patient is an individual who has an external conduit, which is directly in contact with the heart. For example, you're looking at pacing wires, saline-filled catheters like the artery line, the center line, the pulmonary artery flotation catheters. So that's what is required. So there is a connection directly with the heart, and the solution within these catheters are conducting material. So saline is used, which is a conducting material. But for example, pacing wires are conducting material themselves. So microshock can happen in any of these situations. So first we go through macro shock, which patients and staff both are at risk. And to understand that, we need to look at how the current flows in an equipment. So when you plug in an equipment, there are three, terms to it. You have a live, the neutral, and the earth connections. The current will flow through the live wire, does work, returned back by the neutral into the earth. That's where it is dumped. Okay. And you see that at the substation, the neutral and earth are connected together, and that's because whatever is returning back has to be returned back or dumped into the earth. Earth is like a big reservoir for this current. So when you touch the equipment, nothing will happen as long as the current is flowing from the live wire, returning back by the neutral into the earth. Nothing happens. But if there is a disconnection and the live wire comes into contact with the body, now if you touch it and you are standing on the earth, that is, there is no insulation between your body and the earth, then the current will flow back through the earth to the earth where it is attached to the neutral at the substation, and then you will get a shock. So that's how macro shock actually happens. Okay. What is the effect of this current flowing through your body? That depends on the Ohm's law. What is the frequency? What is the current? So when we look at the current and frequency, now the frequency at which the household current or the current in the your operation theaters and the hospital supplies at 50 hertz, and that is actually called the your dangerous current. That amount of that frequency can sync with the heart and cause ventricular fibrillation. But what's so important, this graph is very, very important, because if you can see, as the frequency increases, the greater amount of current can flow through the body without actually exciting the tissues. And this is used in diathermy. So diathermy uses a very high current. It burns the tissues, but it does not excite the heart. It does not cause fibrillation. But if it was at a 50 hertz or 60 hertz, you apply to the body that current, you will cause ventricular fibrillation. So the 50 hertz, so when the frequency at which the household current, it's at 230 volts at 50 hertz or 130 volts at 50 hertz. Now the lower frequency current does not cause heating. So that's why the transmission wires are at 50 hertz. If it was used at a much higher frequency, which was safe for a human body, then the wire would heat up and they will melt away. So that is important, that we don't want that happening. That's why the current is transmitted at 50 hertz. And that's a dangerous frequency. Now, if a 50 hertz current was to pass for 1 second through the body, what would it do? Now, if it is as low as 1 milliamp, it will just cause tingling. 5 milliamps, it can cause pain. If you want to actually see it, apply a Rain of 4 monitoring yourself, and you can experience it. I did it very recently. 15 milliamps, it causes severe pain and can cause local muscle spasm. At 50 milliamps, the respiratory muscles can go into spasm. Okay, you can stop breathing. but you require a current of around 80 to 100 milliamps, which will cause dysrhythmias and cause the heart to fail. So you need that higher current, 80 to 100 milliamps, to pass through the heart to cause dysrhythmias. But we have natural protection. And what are these natural protection? The first of that is that we are awake, and our automatic and intentional reflexes will make us move our hand away from the component which causes that. The second thing is the skin. Skin has got very high resistance. Obviously, dry skin has much, much higher resistance than the wet. So if you have dry hands, you're touching anything, okay, the chances of high current passing through your body is very, very low. It's only when you have your hands are wet that the current flow increases, or you're sweating again. Sweat has a lot of sodium chloride, so it's a good conductor. Sweat is a good conductor of electricity. Unfortunately, that's what happens when somebody comes in accidental contact with a live wire. Okay, they will become afraid. The autonomic system will kick in. They start sweating. They are scared, and that itself increases the conduction through the body and makes things worse. But why are patients at risk, greater risk? Very simple. They are anesthetized. They can't move. They can't react. They might be even say in the intensive care, tube sick or bedridden. Their automatic intentional reflexes are completely absent or slowed. Then in operation theaters, the surgeon uses a skin prep. So you have got a skin which is wet, or the blood is there. There's fluid, there's wash. And so you are making the skin resistance very low. And then again, we intentionally connect patient to electrical circuits. And a patient is connected to monitors from anesthetic side. The surgeon is using a diathermy. So you are actually increasing the risk to the patients. So are we able to prevent these electrical hazards? The answer is no. We can minimize them, but we will not be able to eliminate them at all. Okay. So idea is to minimize these hazards. And we can take precautions. So precautions against macro shock. And we can look at the main supply. We can look at the equipment, how we can make them safer. We make sure the main supply, there's maintenance, regular maintenance is there. We use something called isolation transformers, which supply us the safe electrical supply. Okay. And in the equipment, there are different things. We can use isolated circuits. Equipment should be earth. Earth is a double-edged sword, and I'll come to that. And each equipment has got an associated electrical safety symbol, which actually says that this particular equipment can be used only in certain situation. Okay. What about safety against microshock? Again, we can look at the same thing, equipment. We don't want to use earth, so that you can see that the earth is dangerous for the microshock. So if you want to prevent microshock, you need to use isolated circuit which do not have earth. And again, if the patient has got a CVP or got an artery line, there are particularly particular electrical safety symbols associated with that equipment. And you need to make sure that those equipment are only used when the patient is connected to these. So what are isolated transformers or isolated power supply? Okay. So this is a station. This is one of our intensive care units. This is an isolated power system. So what exactly is isolation transformer? So if we have alternating current flowing through a coil, a primary coil, you bring in another coil in the proximity of that, and you can induce current in the secondary coil. So what you're doing here, you are actually isolating the secondary circuit from the primary circuit. And why is this important? And this is important because of the fact that at the substation, the earth and the neutrals are connected. And the earth is a good source of, it contains a lot of conducting material. And this return path is important. So if a person touches the live wire, if he is standing on a non-conducting material, then the current will not flow. But if you take away this conducting material, and say patient is standing on a pool of water, the current can actually flow through the body to the your earth, complete the circuit, and patient will get a shock. So once the return path is completed, patient gets a shock, and that's a dangerous thing. But if you have an isolated power system, now we don't have a live and neutral in the secondary coils. We just call it line 1 and line 2. Now here the patient is standing on the earth, he's standing, but then the circuit need to be completed between line 1 and line 2. So even if he touches line 1, nothing will happen to him, even though the current is flowing to the earth. So there's no completion of circuit. The completion of circuit here need to happen between line 1 and line 2. And if that happens, then obviously the patient can actually get a shock. And that's very unusual to actually do that. Somebody coming in contact with line A and line B both together. And that's why isolated power systems are considered to be safer power systems in that. But if somebody actually foolishly does this, that they do exactly what is happening at the substation where the neutral is linked to the earth, and they try to link the line B to the earth, and then it's no difference then. This is not an isolated power system. So if the line B or line A is earth, once you attach the earth to the secondary circuit, it is no longer safe. And this does not, now it's no longer a isolated power system. So for isolated power system, the secondary source of power need to be earth free. That's the definition of a floating circuit. So for this is very, very important. We need to remember this definition. For isolation system to be safe, it should be earth free. That is what a floating circuit is. This is also definition of floating circuit. A floating circuit is free from earth. So we did say that earth and ground is a safety feature or a hazard feature. So there are different type of earth. I'm not talking about the universe, but the symbols associated with earth. So you have a symbol like this, which is just normal earth. Then you have an earth symbol, which is surrounded by a circle enclosed within a circle. This is called a protective earth. And then you have just a circle within an inverted triangle, and this is called an equipotential earth. So you need to know these three symbols, and you will see it at different places. Now, if you look at this back of a machine, what we have here, that is the earth, okay, and that is the equipotential earth. And on the other side, the lower one, which I've shown, where you see a green wire, you see a earth enclosing that, and that is called a protective earth. And you can see that the earth wire is now attached to the body of the machine. So that is called a protective earth. So the earth, which is where the plug is put in, that is just the normal earth. So how does an earth protect us from microshock? So we have this equipment where the neutral wire has become disconnected. You plug it in, and the current is now, there is some kind of connection between the live wire and the body of the equipment. Now, if you actually touch it and the current flows through you and the circuit get complete with the earth, you're going to get a shock, right? Because you become the path of least resistance for the current to flow through, and this will call a microshock. But what if the body of the equipment was earth? If this is done, this is known as protective earth. So Even if the neutral wire is disconnected and there is a leakage or there is a connection between the live wire and that, the current will complete the circuit through the earth because that becomes the path of least resistance. And what you will see is that only very small amount of current may flow through you. So instead of getting a shock, you might actually just feel a tingling sensation on your hand. And that's all. Like you remember that if you have a current flowing around 15 to 50 milliamps, you might actually get a tingling sensation or get a little bit of motor response from your hand, like as if you're using a train of four on yourself. Okay. So in brief, the earth or the ground protects us from macro shock. But can earth connections be unsafe? And that's very, very important for patients. Now you have a patient who's, this is the external pacing unit. The patient somehow get earthed, okay, because he's lying on a bed and his hand is or leg is touching the rails, which are in contact with the earth. Okay. Now this is if this is a isolate but nothing will happen. But what if the pacemaker also is earth? So the body of the pacemaker is conducting and it is actually sitting on a trolley, which is again in contact with the earth. Now, if anything, if there is any leakage of current through the heart, the patient then can get shocked. So isolated power systems are important when you have any connection with the external unit directly to the heart. So earthing is, it's not safe. But what if you have multiple earthings? Okay, because patients will not just be connected to pacemaker, you will be connected to ECG because that's how you're going to monitor if the patient is having the effect, or how do you monitor whether the pacemaker is working or not. So you never actually have patient connected to a single monitor in most cases. The current will always flow from a higher potential to a lower potential, just like the water actually does. So you have to remember that. Now imagine a patient who is connected to multiple equipment, and all of these equipment have got an earth. Now each equipment leaks a current, but that is not going to be similar. They're going to be of different potentials. And when this happens and they flow through the body, they can form their own circuits. And if this current flows through the connection, which is directly to the earth, then patient will have a microshock. Even with a small amount of current, patient will get a shock, a microshock. Patient can go into ventricular fibrillation. And you say, oh, nothing has happened to the patient. Why is it that's happening? This could be because of the multiple earth connections. So it's very, very important in operation theaters that all the equipment that is connected to the patient is earth-free. Okay. So what is equipotential earth? So we talked about three earth, the protective earth, and the equipotential earth. And what is the importance of equipotential earth? Now, if you have three containers with different levels of water, individually, okay, the one which has got a large amount of flow with a greater force, the small with lesser force, and so on. But if you want to bring the water levels to the same, what you need to do is connect them all together and have a single outflow. You will see that after some time, everything will come to the same level. That is what is called equipotentiality. Okay. So how do we actually do with it within patients? I'll come in a minute. So to protect the patient, it's important that the circuit that is attached to the patient is always isolated from the earth. That is, we use isolated power system. And when earth connection is unavoidable or it happens accidentally, then a single point is okay, but it should not happen at multiple points. So every equipment that is connected to the patient has a symbol associated with them. Okay, I don't know whether you're able to see this clearly or not. So you have the ECG, which has got a heart inside a box. You got the pressure transducer area, which is again heart of the box. ECG or SpO2 has got a man inside a box. Okay. I'll show you some more of them much more clearly. This is the pressure transducer cable. You can see a heart inside a box with cables. Okay, you can actually also see that with the ECG. And then there's a fluid, back of a fluid warmer. They can see a man and you can see a droplet. Okay. This is a diathermy machine. You can see that there's a droplet and then there's a heart inside a box. This is back of a machine and it says class 1 type B. And there's a man in the box. And these are other symbols like you have transducers. You have this equipment which has got AP in a green circle, a man, and then this is behind the infusion pump again. It's a IPX4, and there's a double box. There's a heart inside a box, man inside a box. There's IPX7. Okay, infusion pumps again. You see those symbols everywhere. Again, the bear hugger. Okay, it's bear hugger. There's a equipotential earth. There's a man inside a box. This is a ripple heat system. It's a very old system. Let's say APN thing. Okay, a nerve stimulator used for regional anesthesia. Man inside a box. So how are the devices classified according to the safety? This is very, very important. Okay, so there are various classifications. There'll be classification by class 1, 2, and 3. There's classification by type B, BF, and CF, and then the classification called APG classification, which is suitability for use in flammable atmosphere. Now, we don't actually have that in theaters, but again, in certain equipment, you'll find that. And then there is protection against ingress of water, or also known as the IPX classification. So what is class 1 and 2? Class 1 is basic insulation of any equipment, and there's so this is an equipment which can come in contact with this stuff. The class 2 is the only one which has got electrical symbol, and this is a double insulation. So there's a primary insulation or the basic insulation, and then you have a covering of another insulation. So that's double insulation. And then you have class 3 equipment, which use something called safety electrical low voltage, or SELV, which is maximum of 24 volts for AC and 40 volts for DC. And this is the reason what they use is that if they come in contact with the patient or the staff, then they shouldn't cause macro shock. Okay. Most important one is classification by type. And it is said that all diagnostic, therapeutic, life-supporting, or patient handling equipment must comply to this class, that they should be type B, BF, or CF. Okay. And what is they're based on? What is this classification based on? This classification is based on permissible leakage current. So that comes to a question, what is a leakage current? I had explained in the past, in the just a few slides ago, when you have an equipment, the current flows through the live wire, it then returns back via the neutral. So leakage current is the current, any current that does not return back via the neutral is the leakage current. And this current will find itself either going to the body of the equipment or flowing back through the to the substation. So any current, the simple definition is that any current that does not return back via the neutral is a leakage current. And every equipment, however new it is, will leak some current. It can happen because of the conductance. Okay, like I explained to you in my basic lecture, that what is a conductor or capacitance. So capacitance current, by inductance, because we use, most of the time we use AC current for powering the equipment, so they can induce current. Or it could be from wear and tear, the equipment fall, they get moved, and there is insulation coming off. So with wear and tear, with time, there will be some amount of leakage current. And that's why all equipment are checked for leakage current from time to time by the biomedical engineering department. They all go for servicing to see if they have exceeded the amount of leakage current or not. So if you see a body on any equipment, then it is type B. So B for body, okay? And this can be applied, I mean, it has got many applied for, and I'll show you what the examples are. But the maximum permissible leakage current in these cases is less than 500 microamps. And this is the current that is below the threshold for skin sensation. So even if this current flows through your body, you don't even feel the tingling sensation. So this cannot cause any pain or injury, right? So equipment like thermometers, manometers, gas analyzers, ventilator alarms. Now they don't come in direct contact with the patient, even though they are somehow connected to the patient, but they're not coming in direct contact. So these types can be type B. But if they are coming into contact with them, they need to be, type BF. So body with a floating circuit or isolated circuit. F is for floating or earth-free circuit. So these are suitable where surface electrodes are used. So they are coming in now direct contact with the patient. And the only safety feature here is the normal skin resistance. So if they are dry, then it is. The maximal permissible leakage current in this one is also 500 microamps as in B, but the only difference is that these machines use isolated circuit. That is circuit which is floating or which is free of earth. So that is type BF. And forced air warmers, blood warmers, nerve stimulators, these all can be type BF. The next one is a heart inside a box. So this is type CF. C is cardiac with a floating circuit. So there's no type C. There's only type CF. So this is the most stringent protection that can be applied against the shock hazards. So anything which are connected to the heart directly or indirectly are type CF. And the maximum permissible leakage current in this setup is 1/10 of what B and BF is, that is less than 50 microamps. Okay. And anything which is more than 50 microamps can cause, microshock. So that's why the maximum allowable leakage current is less than 50 amps. So ECG, EMG, EEG, pacemakers, anything, fluid catheters, anything which is coming in direct contact, even syringe drivers, pressure transducers, all those need to be type CF. The next is zone of risk. Now, this was important when we use flammable agents like ether, which was flammable. So if you look at the machine and the connection with the patient and your expiratory valves, the concentration of gases in those regions is going to be pretty high. So these are highly flammable zone. That is within the 5 centimeters. And equipment which need to be used need to be APG type, okay, anesthesia-proof gas. But as we go further away from that, so between 5 to 25, you can have equipment which is anesthetic proof. That's because as we go further away, the gases with the flammable gases will get diluted with air, and hence they are much safer to use. So depending on suitability for use in flammable atmosphere, the equipment can be AP. And these can be used in the zone of 5 to 25 centimeters from the enclosed medical gas system. And this device must not be capable of igniting any mixture of explosive anesthetic agent with air in normal use, because that's what is diluting the anesthetic gas in that atmosphere. Whereas when you are closer to the patient, the concentration of the flammable agent and the oxygen is very, very high. Also important is the temperature. So the standards may be met by the prevention of static sparks, restriction of temperature. The temperature should not go, or should remain less than 200 degrees Celsius. And there should be fireproof enclosures. Okay, and the energy level should be on the lower side. Now, APG is a lot more stringent because they are very close to the higher concentration of oxygen and with oxygen. And because of the stringent precautions used, they can be used within the zone of 0 to 5 centimeters from the gas system. And there, no device should be capable of igniting the mixture of explosive anesthetic acid with oxygen or nitrous oxide in either a faulty condition or normal condition. So in these cases, the surface temperature is never allowed to go more than 90 degrees Celsius. The last classification is the IPX classification. IPX stands for I is for ingress of water, PX for protection. And these are the common symbols you will likely see in relation to this. You see a droplet inside a triangle or two droplets. And they can be also, we say the single drop is drip proof or IPX1. Splash proof is IPX4 and watertight is IPX7. So that's most stringent one is IPX7. So to summarize and come to the end of the lectures, you need to know what is the difference between the macro and micro shock. You need to know what are the safety features required to prevent shock. You should know how the equipments are made safe. And what are the safety classification of equipment? And in the end, don't forget that we can only minimize the electrical hazards. We cannot eliminate it. Okay, thank you guys. And again, ready for taking any questions.
Hello, sir.
Yeah.
Good morning, sir. Thank you for the presentation. I just have a doubt. Sometimes in the theater, when you touch the walls or the doors, which are metallic doors, which are the automatic doors, with the sensor, so sometimes you get the static sort of a shock.
Yeah.
What is the cause for that? The leakage current from the equipment?
No. So that is usually from what you're wearing.
Okay.
Yeah. So there are stringent guidelines for what kind of clothing you can wear and what kind of footwear can you wear.
Okay.
If people do not actually follow that, they can get static charge. Okay. So if you have certain amount of synthetic fibers within your clothing or you have woolen fibers, they can itself cause static charge. And when you touch, so if you're wearing a good quality, shoe, which is highly insulated, then it's not allowing the charge to flow through. So if you look at, there are actually, specifications, what kind of shoes you need to wear. So they need to have insulation, but they also should be able to allow the static charges to pass through the earth.
Okay.
And the older they get, the worse they become, or if you are using on charges. So when you actually touch a door which may be earth or which has a metal, then the charge is actually released through that, and then you complete circuit. That's why you get a charge. So it is all just a static. It's got nothing to do with the leakage current.
Okay, sir.
Yeah.
Thank you.
So
sir.
that's another thing you need to actually also read about a little bit about static electricity as well, and read about what is the specification for the clothes, why we tend to use cotton in theaters rather than synthetic material, and also read, there is actually also specification on what is the resistance in the shoe. Okay, we don't look at it as much. Now they're not as important for main reason that we're not using any flammable agents. It's not ether time. During ether time, even that static charge was enough to actually cause fire.
Oh,
And if you look at the older machines, you would see a chain hanging from the machines.
no, I haven't
Have
seen
you?
it, sir.
You're not seeing it, yeah. But if you actually go into the older machines, again, they were specific. The wheels were yellow color. So when they say, why are the wheels yellow color? That it was the reason. Okay. So that it is anti-static. Okay.
Anti-static.
And yeah, absolutely. You need to have anti-static that do not allow the static current to actually form on you or the machine or anywhere. So wherever the static current is formed, and once it comes in contact with flammable agents, it will cause sparking, it will cause explosions. And that's why when we actually looked at the definition of the electrical safety, fires and explosions are part of it.
Okay, sir.
Okay. But these are more historical
Okay.
with ether. Okay. But now newer agents are not flammable. The only way anybody can cause fire now is use of diathermy and alcoholic chlorhexidine. It has happened in our theater a few years ago, and it is also reported. So that's the only main. So pooling of chlorhexidine in patients where the diathermy is used should not be allowed. So when the people put cotton or cotton wool or things where they're doing a alcoholic prep, that need to be taken away before you clean and drape the patient.
Okay, sir.
Mm.
Thank you so much.
You're welcome.
So I have a doubt.
Hi,
So,
Pankaj. Yeah.
hello. Yeah.
Hi, Pankaj, yeah.
So, yes, sir. How do we assess for presence of any leaks or multiple earthing connections, which you said? I mean,
Yeah.
in relation to the defibrillator, use of defibrillator. I mean, during an emergency, we obviously cannot assess for any leaks. We just go on and shock the patient according to protocol. But then
Yeah.
when it is idle, how do we assess for leaks or multiple earthings?
No,
That
you
we don't.
don't. You don't. Yeah. So leakage current is measured by the biomedical engineering. So that's not it's not important for defibrillator because there you are actually applying current across the chest. So it's fine. It's okay. You're not going to cause any harm. The heart is already in a arrhythmias or ventricular fibrillation or whatever. So it's not important for the defibrillators. Now defibrillators anyway, they don't have earthing. They use a transformers type of transformers. So they by itself, they are using isolated power system. So you're not going to have that. What is important is that when you have the patient is not touching anything which is earth or somebody touching, then that's why we say that stand aside, isn't it? Everybody's asked to move away from the patient when he's shocking them.
Okay.
Yeah. So it's the equipment in the theaters which is need to be plugged into isolated power systems. So if you look at the power supply within the theaters, especially in your theaters, go back and see, it will say IPS. IPS is isolated power system. So the equipment which is connected to patient should always be connected to only IPS, whether it's in the intensive care or in the theaters. They should not be plugged in directly into the normal electrical outlets, the one we use for attaching toasters or coffee machine. No, they're not that one. The power supply to the theaters need to be isolated power, and the equipment need to be connected to the isolated power systems. Any other questions? Anything on the YouTube? Any questions on the YouTube?
No, I just checked YouTube. I think there is only one question by Seema Bashir asking about the table vivas. Do they ask specific part of the syllabus at each table or generally anything? So I've told doctor to join tomorrow's lecture. Let me just go on to the actual YouTube stream and check. I know I've just been checking only on the thing. Give me 1 second.
No worries.
Just to be sure. I
So
want
it's absolutely your potluck. What questions you get. You may not even get asked any questions on electrical safety. It's like anything. There is limited time. It's just your potluck. You might actually get easy questions. It's within the batch, that batch. Everybody will be asked the same questions. And that's how you actually assess people. So particular batches will have the same questions, and within that batch, it depends how you perform within that batch. But between the batches, you could actually have one batch which is asked about electricity, but the other batch may not be asked about electricity at all. The questions can vary. So it's just potluck.
nothing much on that. Chetan, you want to
Okay.
say something?
No, it's okay. I mean, she was beautifully elaborated on the important questions. Yeah, people just need to practice those diagrams and answer it through diagrams and these charts.
Hello.
Yeah.
Hi,
Dr.
Ranjit.
Ranjit?
Yeah, hi, sir. Sorry, I think this might be a silly question, but still, sir, when you are using
No,
this,
no question is silly. Just to everyone, please, you need to be selfish here. Just going to tell everyone here, right? You are the ones giving the exams. You are the ones who are putting the hard work. You are the ones who have paid money for it, right? So don't be guilty of being silly question or any question, right? At the end of the day, nobody cares. Once you pass the exam, you pass the exam. So for which, even if you have to go through something, you just have to go through. So even if you ask a silly question, it is very important that you ask it, right? Rather than being embarrassed in front of the examiner, this is the time you get the most of it, right?
yes, sir, yes. Sir, when
Yeah.
we are doing this lymph node biopsies in the neck, like very superficial procedures, most of the time the surgeon just asks for sedation and they don't want anything else. So the moment they place the cautery, like a few times the patient just went into sudden laryngospasm, right away. Yeah. So is it something wrong, like with the connection issues, or it should be with the plane of anesthesia? Usually, what happens?
Yeah, so I think in those places, they need to use bipolar rather than unipolar.
Yeah.
Okay, so it's not there. It's direct stimulation of the muscles which are very close to the larynx. So
Yes,
everything. So if you when you look at the muscles when they are stimulating the muscle using, they contract.
Yeah.
Yeah, so that's what is happening. So those current is actually causing the contraction of the muscle. It is the direct contraction. That's what is causing. And to do that, they need to use the bipolar diathermy rather than use the monopolar.
Monopolar. Yeah. Thank you, sir.
Anyone else? I think diathermy is a topic on its own for talking.
Yeah, I will. Yeah. I will likely, because the diathermy, there is a lot of confusion which people have, and it's all related to the way diathermy have actually evolved from first generation to the present solid state diathermies.
Yeah.
And there's a lot of electrical safety issues which we need to discuss. That's why that'll be going to be part 3 of lecture, kept it separately. It becomes too much. Even this morning, I was thinking whether I should just limit it to just basics of then I thought that it'll become too less. So I thought I'll cover part of the electrical safety as well.
No, that's right. I think it becomes too much. But this itself, which starts off with an introduction into electricity, if they get the basics right, it's much easier for anyone to go to an advanced level, and learn anything they want. And I think the highlight of this talk from my perspective is those graphs and the charts that you wrote. You made it look simple, and it made even me who have not touched this textbook for nearly 20 years to understand and want to go back and read. So that, I feel like, when a trainee asks me such a question, luckily nowadays no trainee asks good questions. And I'm thankful for them. They don't ask me on electricity or anything. But I feel I don't want to feel ignorant. I need to feel, But yeah, now I'm going to go back to the textbook and go through this video again. And I know you've been
you can direct,
for 2
or you can
decades.
direct your trainees to this video.
No, I won't do that because one, they need more in depth. So I will set up a one-to-one session with you. That will be easier.
Yeah, absolutely, absolutely. People can pick up. The best thing would be to actually take old questions from the question bank.
Yeah.
And then come to me, and then have just a session on that.
Yeah.
I used to do 4 hours of physics. So this used to be, I think, 3 hours session.
Yeah.
And then 4 hours on equipment as well. So physics, Viva.
Yeah.
A lot of people actually who are now consultants, they have mentioned that they used to attend my lectures. That used to be the start of the Mercy's, the Viva course. They used to start with my lectures.
That's good. Look, it's coming back to basics. I think it's exciting and also a bit motivating. But because the excitement kicks in more than this thing, I would love to go back. Excellent lecture. Really appreciate this one. I think more will come on the FRCA series, which will be starting soon. And we'll kick off with the EDAIC II prep with a mock Viva tomorrow between the 3 faculties. So they will do the Vivas and explain how the Vivas go through. And from there upon, there will be a mix of didactic lectures and Vivas. Thank you very much, Shiv.
Okay, guys. See you then. Have a nice day.
Yeah. Thank you, everyone.
Bye. Bye.